This is Statistics 243 at Berkeley for Wednesday, October 22nd. All right, let's go ahead and get started. So I'm going to pick up where I left off in going through this demo with Spark. And what we'll see is just some of sort of the logistics of managing these distributed clusters, and we'll see some of these basic MapReduce kinds of steps. And hopefully at the end we'll get to not only having seen some sort of pre-processing and data set kind of operations, but also see a little bit of model fitting within this context. Okay, so as I mentioned in the posts on Piazza, you guys are going to be doing all this yourself for problem set 6. And you'll be able to follow a lot of this template code, hopefully fairly closely. Particularly for the Spark stuff, I'm not going to ask you guys to do a lot new relative to what I did. I'm sort of just going to ask you to sort of replicate sort of what, more or less what I've done with a few tweaks. And I may come back to some of this when we get to the optimization unit and ask you guys to do something more involved, but we'll see about that. Okay, so the other thing I want to mention here is I think for the most part, almost all of this stuff where we're doing cloud computing and this distributed distributing computations across nodes and whatnot is probably new. Almost all of it is probably new to almost everybody. So in general, I invite questions, but particularly, if you have questions, even if they seem very simple, just stop me and ask. Okay, so again, I'm going to try and manage this process of not trying to take too much time of waiting for 5 minutes for the next thing to happen. So we'll see if I'm able to juggle that. Okay, so I've started up I'm in my virtual machine on the laptop. I've executed the Spark commands, basically some shell commands and some Python commands that the Spark folks have created for us. I've executed the startup script that has those commands in it to start up a cluster of 1 master node and 12 slave or worker nodes. And after I've invoked that command, at the end of all that, there's pages and pages of output showing all the stuff it's done. And at the end of it, it gets to this point, and you'll see something like this. And then you'll be back at the command line interface for the VM. And so at that point I say, okay, now I want to use that script, except I'm going to use it to log into the VM. So this is basically equivalent to just SSHing to the master node of the virtual machine, of the virtual cluster. Because I'm on my own virtual machine here, I'm SSHing from this virtual machine to the master node of the virtual cluster. Okay, so once I do that, then it's sort of like we're just on any old Linux machine, and I'm going to do the commands that I think I showed you guys last time. To basically, I need to move the airline dataset files from my disk space on the SCF network onto the master node. So that's what I'm doing somewhere in here. There's an SCP. So there's an SCP here. And then I need to move them into the HDFS. And so I've created this /data directory and /data airline in the distributed file system. And then once I've done that, and I'm just going to download 3 of the files from the airline data set, just so hopefully this will go quickly enough for a demo. And now, just sort of catching us up with where I was. Where is it? Oh, so I've done the copy from local command in this Hadoop command. So this is sort of a subcommand of the Hadoop command. And I'm copying those bzipped airline data files from the disk space on the master node into the distributed file system. So that's what that's doing. And then once I've done that, I can check on it and make sure that those files indeed are in there. So then I'm going to issue the ls command, but within the context of doing it on the distributed file system. And so I ask what's in there, and it says, okay, you've got 3 files in there, and those are the files. And so the basic idea of all this is we have some set of files that make up some very large data set. We can treat each of the rows as individual observations, and when we're working with stuff on the distributed disk space, we basically want to basically have that huge data set split up across all of the nodes in some equitable way. So it turns out that if we just load files in like this, I believe basically each one of these files is sitting on one of the slave nodes. So we haven't actually distributed all the data across all 12 of the nodes. They're only distributed across the 3 nodes. So things are not very well balanced at the moment in terms of how the files are set up on the disk space. And we're going to see some ways to try and start to address that. Okay, so that was sort of recapitulation of where we stopped off last time. So are there questions about sort of the big picture of the setup here, or what we're trying to do here? Okay. Okay, so now I'm going to start up the Spark interface, the Python interface for Spark, and I'm just working through the Python file that's in the repository. And so it lives, that executable lives in root Spark bin, so I'm adding that to my path, and then I can just type in PySpark, and that will start up my Python session. But it's starting up a Python session basically where all of the information about the Spark setup is already sort of instantiated in this object that's called SC, and that's this Spark cluster object. And so when we start to do things, we're going to start to operate on that SC object that's already loaded in automatically. Okay, so I'm going to import NumPy because I think I need to use that later. There's this function add, which is basically just a drop-in for the plus sign, for the plus operator, that I'm going to use later as well, so I'm going to import that. And then I'm going to start reading stuff in. And so I'm going to need to figure out how do I read stuff in. So here I am at the Python command line. I'm just doing sort of standard Python things. And now I need to read in the data set. So the way that I read it in is there's this command called text. There's this method called textfile that I apply to the SC object. So again, we're in this object-oriented programming paradigm now. And I tell all the data is living in individual files within this directory. So that's where I'm going to go and get the data. And I'm going to change this around for the moment. So I believe what will happen if we just read it in like this is because the data started out in 3 separate files, that what will happen is that the data, once it gets read in, will be sitting in 3 separate, these things called partitions or chunks of the data. And so the problem with that is that if I then start to try and do parallel operations, the parallel operations are basically done on these chunks or these partitions. I have a network of 12 nodes. Each of those nodes has 2 cores on it, so I have 24 processing units. If I've only split up my data set into 3 partitions and I try and do it in parallel, sort of the obvious limitation of that is it's silly to do things, it's silly to have 3 processes going when I could have 24 processes going because I have 24 cores. So the idea of repartitioning is to try and sort of manipulate the data set. I'm basically reading it into memory, but I want to make sure I read it into memory distributed in enough chunks that I can have at least 1 chunk per processor that I have available to me, and I have 24 processors. So I'm actually going to repartition this into more than 24 chunks. So so I've already sort of explained why I want to have at least 24 chunks that I partition into because I have 24 processing units. So why might I want to have more than 24 chunks?
Well, the balance of load later.
Okay, so again, it's the same sort of thing we've talked about before. But we want to try and ensure that there's some load balancing. If I have 24 tasks, end up having 24 chunks, maybe one of them will go a little bit more slowly, and I'll be waiting for the slowest one. Whereas if I divide it up into more tasks, it's more likely to be able to be more reasonably well load balanced. I am going to use a multiple of 24 just under the thought that if they do more or less take the same amount of time, then maybe the first 24 will finish, and then the next 24, and the next 24, and the next 24, and I won't be waiting for one lagging one that gets started when all the others have finished. So there's some consideration of that. I don't actually know, and I think one of the extra credit problems that I'm assigning for problem set 6 is to say, play around with this. What if I use 24 here versus 48 versus 96 versus 192 versus 10,000 or something? How much of an effect does that have? I don't actually know. It'd be interesting to try that out a little bit. Okay, so I'm reading this. I'm reading this in. You can see I can chain together these methods. What this is going to do is this is going to create one of these dataset objects that are called these RDDs, or resilient distributed data sets. That's also going to be a Python object. So the result of this is a Python object. If I then do dot on the result of this, I'm now applying the repartition method to one of these RDD objects. Okay, so again, I'm chaining together these commands, but I'm still working in this on this object-oriented paradigm. Huh, that's unfortunate. So it looks like I've completely exited out of the cluster. Okay, well, hopefully that won't happen too much, because this could get to be a pain if it does. Okay, so I'm back in Python, hopefully, and now I'm going to... Okay, so I've done this. If I just type lines, it says, oh, that's one of these RDDs. I don't know exactly what all of this result that came back to me means. The other thing that you might have noticed is this went from here to here in a matter of a millisecond or a half a second or something. So it's pretty clear that if this, presuming that this is a big enough data set stored here, that all of that was not read off of the disk into memory just like that. So that when you see something like that, the next thing that you should be thinking is, maybe there's some lazy processing going on, and it hasn't actually done that process. It's just sort of stored up the fact that eventually it may need to do that process, but it hasn't yet done it yet. And that's indeed what what's going on here. Is it has some lazy evaluation going on. Okay, so then the next thing we might do, just as a very simple first operation, is we've got this resilient distributed data set that's, yeah, Mike.
When you're doing the repartition, are you thinking about how big each of those partitions are with respect to the amount of RAM you have?
Yeah, so that's a great question. So I sort of motivated this last time some by saying that Spark is basically this idea of having in-memory Hadoop. And so, one of the things we're going to have to think about, we would want to be thinking about, in this case we don't have to think about it too hard because this entire data set will fit in memory across these 12 nodes, but if you were doing this de novo on your own data set, if you wanted to keep everything in memory, you'd want to have a big enough cluster such that the total memory could fit the entire data set in RAM. In terms of the partitioning, I don't think that will matter as much because regardless of whether it's in 4 partitions, well, you need to get enough partitions so that they're spread out across all of the nodes, so you're collectively using all the memory. But once you get to that point, I don't think it matters whether you then have 24 versus 48 versus 96 because it's just a matter of how many chunks there are, but they're probably using up collectively about the same amount of memory. Yeah. Other questions? Okay, so now I'm going to just do this very simple method count that gets applied to this RDD lines, which is the result of doing this, of doing the repartition, of doing the reading in and the repartitioning. And what we should see, arg. I don't know why that keeps happening. All right, well let me try this once more, and if this happens again, I will give up and just go back to the PDF and just walk us through what happens when I do this outside of the VM. Hopefully this will also not happen in the VM for you, because if you guys are doing your problem sets, that's going to be really annoying. So I will try and investigate this a little bit more. Okay, so now you see it's sort of churning through a bunch of processing, and it starts talking about adding pieces into memory, and if we looked at this, what we should see is it's talking about different things happening at different IP addresses. So those are the IP addresses of the slave nodes where each of the operations is going on. And the other thing that we'll see that's a good thing to watch out for, there's a lot of stuff here that I don't actually understand what all of it means, but I'm going to try and just focus on a few things that I think are helpful, that I've sort of found to be helpful when I've been looking at this stuff. So you can see here that it's talking about finishing tasks. And it says it's finished task 0, so the counting starts at 0 rather than 1, in 18,000 milliseconds, so in 18 seconds. And the reason that it has 3 is because it's reading from these 3 files, and so there are really only 3 processes going on the slave nodes. And hopefully, okay, so there it finished task number 2. For some reason, that one took, oh, I know why. That one took a lot longer because the file sizes are not equal to each other. So the 1987 data set is much smaller than the 1988 or the 1989. So a couple things to notice here. First of all, we saw that it was finishing the 0 out of 1, the 0 out of 2, the 0 out of 3 somewhere up here. So I need to scroll a little faster than that if I'm going to get to the top. So am I going to be able to find that? Yeah, so one of the problems with this is there's so much output it's hard to see here. Okay, so you can see if we sort of zero in here, it says, okay, finished 1 out of 3, 2 out of 3, out of 3, out of 3. That was the delayed evaluation of reading in the data set from disk into memory. And now there was the repartitioning. You can see it's starting to mention, it seemed to indicate that it's doing the repartitioning. And then, so for the repartitioning, we now should end up with 96 different tasks because we're repartitioning into 96 blocks or partitions of the data set. And so as we look here to see what are the tasks being finished, it'll say, you know, it's starting task number whatever, finishing task number whatever, 3 out of 96, up through presumably at some point 96 out of 96. So it shows us that there, and it looks like it sort of combined the repartitioning and the line counting, I think, unless I missed a big block of output here. And if we now look in numlines, that was the output of doing the counting, and it says, okay, there are 11 million lines or 11 million observations in this data set that I've been working with. So the other thing to notice here is for some of these operations, it's basically going to do a manipulation of the data set, and it's going to produce a new version of that data set. And that's still going to be sitting in memory, sort of in the inner guts of Spark. It's actually sort of sitting in Java. But some of the commands are going to sort of collect an aggregated result back to the master process, and it's just going to be available to us as a standard Python object. And so numlines is a simple example of that. That the result of this is it just gives back a scalar into Python, and this is just a Python object. It should just be a Python numeric value. Okay, so I think that's all I have to say there. Maybe if I keep hitting return here to remind it that I still exist, maybe that will help. Any questions before I go to the next thing? Yeah, Kelly.
Yeah, sorry, maybe I missed something. So you said that this stuff is sitting in Java?
So all of this is executing natively in Java.
Okay.
So we could actually be writing all this code in Java or in a language called Scala.
Okay.
I should go look up. I don't quite understand the exact connections between Scala and Java. But basically what's going on here is whenever you execute some Python code, the objects in the RDD, I think, are sitting in Java objects. And so when you execute Python code, what it has to do is go in, serialize those objects, basically make a representation of those objects that can get copied into Python objects. Then the calculations are done on the Python objects, and if we're still doing stuff with the RDD, the results would get put back into the RDD. Again, they'd have to be transferred from Python to Java objects. So there is some overhead in doing that, and when I asked some of the Spark folks over in computer science, I didn't get a firm answer of sort of how much faster it was if you were doing this in Java or Scala versus Python. Python's going to be slower, but it seems like the rule of thumb might be like maybe it's 40% slower to do in Python, which to me seems like an acceptable trade-off relative to having to learn yet another language, right? So, okay, other questions? All right, so here's our very first sort of more standard MapReduce calculation that we're going to do here. And what do I have to do? I have to define a map function. And I should say what I'm trying to do here. I just want to count up the number of flights for each of the airports where the flight would depart from. Okay, so basically sort of a stratified calculation. Obviously, it's a very simple calculation on the different strata or subsets of the data. So if I want to do that, one way that I could do that is I could do a reduction for each key, where the key would be the airport. And the reduction I'm going to do, any reduction operator basically has to be an operator that can sort of work naturally in parallel. It can't matter what order I send the individual items into the reduction operator, and it can't matter sort of if I do these two first and then this third one and then this fourth one, or these other two first and then this third one and this fourth one, because of the fact that it's just basically taking this huge data set and then it's just adding sort of it's sort of grabbing whatever observations it can in the different distributed chunks. It's doing the summation and then it's summing from the results of those chunks together. So it has to be able to operate in this additive and commutative fashion. So addition is a standard thing that we could do in this reduction paradigm. But if I want to do that reduction, then I need to set up my data set such that I have the keys and the values. And so I basically need to first do a mapping step where I take my original data set and map it to a new version where I now have key value pairs so that each observation has a key associated with it. So that's what this stratify map function is going to do. So what am I going to do? I'm going to take in each line, which is the line from you can think of it as the line from the original CSV file, the observation for each flight. I'm going to split it up by column because this is still just in a text form. There's nothing magic that's happened here to convert it into numeric data or anything. It's just text, a line of text for each observation. And then what am I going to do? Well, in this simple operation, I'm just going to return back the 16th field. Actually, this is the 17th because Python counts from 0. The 17th field should be the departure airline. So the first thing I return back from this operation is going to be interpreted as the key when I then do this reduce by key operation. And the second thing I'm going to return back, I could return back anything I want here. I could return back a vector of a whole bunch of different values related to all the flight information. In this case, since I just want to do counting, I'm just going to return a 1. So I'm basically creating a huge data set that's just airport 1, airport 1, airport 1. And then when I want to do the reduction, I'm going to what it's basically going to do is going to take all those keys that are the first column, group on them, and then sum up all the values in the values. But all the values are just 1, so it's just counting up however many there are. So if I then want to do this, actually I should start this. I should remember to start these well in advance of when I want to get the result back. Okay, so we'll go ahead and let that go. You can see it's working through the individual tasks, and there are going to be 96 of them because of how we've partitioned the data set. So let's just look back at this. I guess I've already sort of described this. We're doing a map step where we take one RDD, which is the version that just has the CSV lines, and transform it into another RDD where we have the key value pairs. We still have a single observation for the size of those two RDDs is the same. And then we pass that second RDD into this reduced by key. It knows that the first thing is going to be the key and the second thing is going to be the value in any given observation. And so it can then just use this addition operator to then add all the ones. That actually produces yet another one of these RDDs. It's going to be a much smaller RDD because it's just going to have as many observations as there are unique airports. But we can collect that whole RDD back into Python as just a standard Python object, and that's what the collect is going to do here. Okay, so since I subset the data set so it's fairly small, that didn't take too long. So let's go ahead and look and see what results looks like. Before I do that, any questions? Yeah, go on.
So are all the three IDs that you said, are they stored in memory? Right?
Yeah, in fact, we now have the 96 because we did the repartitioning. So I'm not sure the 3 ever got read into memory and just sat in memory. I think it might have done some optimization where it basically saw that I wanted to take the 3 and do the repartitioning, and I'm not sure that the 3 still exist in memory. But the 96 chunks definitely do. You might see sometimes if you get sort of going back to Mike's question, if you sort of get it wrong and you get cases where you can't store the entire thing in memory, what I was seeing at some points when I was playing around is I don't remember the exact language that it gave me, but it was basically saying reading blah from memory, reading blah from disk, or no, reading blah into memory, writing blah from memory, and it was sort of giving some indication that it was doing some writing between disk and memory, and when that happened, things slowed down a lot, which makes sense. So that was sort of an indication that I might not have done a good job of making sure that I have enough memory to store the various RDDs in memory. Other questions? So now if I look at results, That's odd. Oh, result, good. If I look at result, what you'll see is it's this Python object that looks like a list of, did Jared go over what tuples are in Python? Yeah, okay. So this looks like a list of tuples. You can just think of it as a list of lists, where it's counted up all of the different keys, but I defined the keys to be the different airports so we can see, you know, how many departures there are from each of the airports. You'll notice what's going on with this. Is there an origin airport? Anybody guess what that is? Yeah, it's the header field from the original 3 CSVs. So that's something to keep in mind, that we have to deal with the fact that that's distinct from these other ones. In some cases like this, it sort of works out naturally because those rows are different than the standard observation rows. But in some cases, we might have to screen that out explicitly. Okay, so that's the sort of thing we could get back, and then we could do, you know, if we wanted to do some analysis in Python, we could do some analysis in Python. We could export this to R. We can do whatever we want with it at this point. Okay, so let's see. There's just a little bit of sort of checking here. I think I'm going to skip over that. The other thing that we could do is, the other couple things I want to mention is we don't have to do all of these operations chained together as one single operation. What I could have done was I could have said, okay, I'm going to do that first mapping step and return the result as one of these RDDs. And then to that RDD that I create, I'm then going to do the reduce by key. Okay, so I don't have to chain. I can sort of chain as many as I want together, but I don't have to chain things together. And then the other thing that's worth keeping in mind is to make sure that Spark knows to keep these interim RDDs in memory. What you sometimes want to do is basically add another method on here, cache, and that basically says keep those RDDs in memory. It's not totally clear to me that if you don't always do this, that it seems like it's not necessarily putting all the stuff back onto disk and sort of erasing it from memory. So I'm not totally clear on when exactly you need this, but that's something to keep in mind as a general principle. This idea of that you may, in some cases, need to tell it to keep the data set in memory because you're going to go back to it and use it again, and you don't want it to have been written to disk and then have to be read back into memory because you're just going to, if you're going to be accessing it over and over again. Okay. So then another thing that we might want to do, another operation in this syntax is, suppose we just want to do a subsetting operation. So in the syntax of Spark, that's called a filter. So we could take our original lines object. Let me go back and remind it that I'm still here. We could take our original lines object and apply the filter method to it. And here's a little bit of different syntax. To do the filtering, you can sort of think about what sort of function we would naturally need to do filtering. We need a function that reads in a line and tells us whether to keep it or not to keep it. Right? So this is an anonymous function, which in Python is called a lambda function, but you can just think of it like we saw in R, like with lapply, we could just define the function on the fly. So that's what we're doing here. We're defining a function on the fly that takes in a line where the input argument is line, and this syntax in Python says, okay, split up the line by commas, pull out the 16th element, which is the departure airport, and then return a true or false depending on whether SFO is in that result. So the syntax is not as familiar to us as what we would do in R, but you can imagine this is sort of the natural thing that we would want to do. So if I did that just like this, you can think of it, what would that do? That would just create one of these, a new RDD that would be a new data set that just has the SFO stuff in it. Okay? But another thing I might want to do is maybe the only reason I'm going to use Spark is just to get my data set down to a manageable size, and then I'm going to go use some other program. So in that case, I would want to save it back out as a file that I could then read in somewhere else, right? So I want to get it off of or I want to save it as a text file back into the HDFS, and then from the master outside of Spark, I could copy from the HDFS back to the master node, just like I copied from the master to the HDFS. So I'm going to save it as a text file. I'm going to name that text file. Actually, let me put that. Oh yeah, I think that will work. I'm going to save it back into the HDFS, and I guess I don't want to say too much more there. So Okay, so it's going ahead, it's chugging along. Hopefully it won't take too long. I'm going to exit out of Java and put it in the background with Control Z, which is what I just did. And now if we do, now I'm just going to query from the master. I'm going to query the Hadoop file system and see what things look like, because I want to see if that file of the SFO data has actually gotten written out. Now it's just easiest just to tell it exactly where it is. Root ephemeral bin. Okay, so it says, okay, it looks now like there's a directory for airline, there's a directory for airline-SFO, and if we look in the airline-SFO, what we see is indeed that there are all these different files in the HDFS, and you'll notice that they start at part 000 and they end at part 95. Why do they end at 95 and start at 0? Right, so there's one file per partition, apparently, is what's gotten written out. So I believe if we copied these back and looked at them, they just would be they would just be in the CSV format, but in 24 separate files or 96 separate files. You know, we could use tools in Unix to then cat all of those into a single file, so that would certainly work. But it's a little bit inconvenient that they're in all of these parts, although it makes sense that they are in those parts. So another thing we could do is we could do another one of these repartition steps, but in sort of the reverse direction of what we already did. I could say, take that resilient distributed data set that's in 16 pieces, that's the SFO subset, and now repartition it into one partition on the HDFS. So it's then going to go in and dealing with the 20, it's going to basically combine across the 96 chunks into one chunk, and the one chunk is just going to be sitting in, I think it's probably just literally sitting on the hard drive of one of the nodes as opposed to being distributed in any way. So I don't think there's too much point in actually showing you that. But if we did that, what we would see if we then did the Hadoop fs -ls command, we'd see there's just one file instead of 96 files. Okay, any questions, comments? All right, so I'm going to go back into Python. I'm hopefully going to go back into Python. Hopefully, so I don't know whether those errors are a big problem or not. They might very well be. Yep, looks like that's not good. All right, so let's start up Spark again and see if we can, as I start to explain the next bit, let's see if we can read it. We can do the lines that we need for the next bit in the background. Oh, I'm going to just force it to do the reading in. I'm gonna use another command called take, and what this will do is this will just pull one of the observations back into Python from the data set, from the distributed data set. So that'll force it to do all the processing, just sort of backwards way of doing that. Okay, so where are we here? So we're in section 6. We've sort of gone through all this business here. About doing some basic manipulations, and I just wanted to mention that I list out some of the basic operations we can do. We've already seen map, and we've seen reduce by key. There's also a reduce that doesn't do the stratification by the different keys. We've seen filtering, we've seen collecting. I talked a little bit about caching, so yeah, actually I guess we've seen pretty much all of these. Okay. So the next thing I thought I'd do is show you a more complicated example. So I've sort of said that when we do these reductions, they need sort of functions that can operate in this associative and commutative manner, where they're basically just simple functions where it doesn't matter what order you do the steps in when you do addition. You can imagine if you were trying to do something like, in this case, compute a median, there's no function that you can't apply the median function in the same way you can apply the addition function. It matters what order you do it in, and you sort of need to have all of the data there available to you to do the median function. You can't do it in little individual summation steps. So, where am I here? Okay, so that did work in terms of collecting one line back. So the idea here, and this would only work if the subsets don't get to be too big, but the idea here is I'm going to, if I want to, this is actually to do the medians for the departure and the arrival delays. And so I'm going to do it where so the idea here is maybe I want to compute the median delay by the air carrier, the airline, the month, the origin airport, and the destination airport. So I want to create sort of a combined key that has all of this information in it. Okay. And so here's what I'm doing is I'm creating this key value that joins the values from those 4 different fields, which happen to be in these particular numeric columns, numerically identified columns. And then this is basically saying, oh, treat the one, if the 0th value in the observation is here, that's the header row, so treat that specially. And if you see any NAs in either the arrival or the departure delays, put a 0 in. And so then the result of this is going to be, the key is going to be this sort of joint key here. And the value in this key value pair is going to be a 4 vector of the departure delay, the arrival delay, or then vice versa, I forget which. And this count variable is basically a 0-1 indicator of whether this is a legitimate observation that should go into doing my median calculation or not. If it's a 1, I know I can use that observation. If it's a 0, it either means that it's a header row or it means there was a missing value. So I want to carry along that sort of meta information about which values are legitimate with me. So I've created this key value pair where I sort of have this aggregate key, and then I have this multiple set of numeric values that are the value. So the syntax, is Python syntax that you're just getting familiar with. But are there any questions about sort of the big picture of what I'm doing here? Okay. So then I need to create a function that will calculate the median. And before I get to that, what I'm going to do here is I'm going to have to do the mapping step with that thing that creates the key value pairs. So that's this. And then I'm going to do a step that says group all of the values that correspond to a given key into one piece. So that group, basically the result of this is going to be sort of an object that has the key, and then it's going to have what's called an iteratable object of all of the elements that belong to that are associated with that key. So this is going to basically be the whole subset of data. Say if the key were SFO, it's going to be all of the observations associated with SFO. And so the trick in this median function is I'm going to have to iterate over all of those objects. So the group by key basically sets things up so I have a key and then the whole subset for each of the airports. And then my median function is going to have to use that iterable object and sort of iterate through it and do the calculations. So let me go ahead and run that, and then I'll come back to what the median function looks like. Might as well do all of it. Oops. Okay. Escape W. Control V. Okay, so now it's going to churn through the processing. So let's go back to the median function. Okay, so I have a couple checks here. I'm checking that the input object should be the key, and then this huge object that contains all the data associated with that key. So I'm just checking that it's actually of length 2. And then input of 1, the first element of that two item object should be this huge thing that contains all the data that I can iterate over the individual observations in. So I want to check that the length of that is bigger than 0. And now what I'm going to do is I'm basically going to iterate through each of the observations that are stored in input of 1. And I'm going to put that in val. So val is now going to be this 4 vector. So maybe it'll help if I sort of lay this out here. So I've got my key value pair. So I have my key, and then I've got my value, which is this whole big object where I've got 4 elements for each of the items in it. So I'm going to this is this list comprehension in Python that if you haven't seen it, that's fine. I don't know if Jerry mentioned it, but it's just sort of Python syntax for like doing an lapply. So I need to work my way through with that for there. I need to work my way through all of these. And then for the second element of val, so val is sequentially going to be this, then it's going to be this, then it's going to be this. So for the second element, which is actually the third element because it's 0 indexed. Oh right, this is, if the second element is a 1 instead of a 0, if it's a legitimate observation, then pull out the 0th element, which is either the arrival or departure delay. And then this is doing the same thing for the other one, the departure delay or the arrival delay. And then I'm just using a NumPy function median on the resulting vector. So each of these creates a vector of, or it's probably a Python list, or actually it's probably a NumPy array, one of these things. It's basically creating a very long list or array of all of the delays, the delay values for, say, SFO. And then I'm computing the median, and then I'm going to go ahead and return that, or maybe I'm going to return a flag that I didn't get a legitimate result. Okay, so questions about what I'm doing here? Yeah, go on.
Sorry, to be clear, the key here is the 14 that like adding together like dash. That's what.
Yeah, sorry. Yeah, I forgot that was my key. Right. Originally, my key was just SFO, LAX, etc. Now my key is the airline, the month, the departure airport, the arrival airport.
And those are always like doing like 1, 2, 3, 4 instead of like some other way, so it's like unique or
Well, I might have been confusing because the key has 4 pieces to it that are just separated by dashes. It's just a text string. And then the actual values, there are 4 values, which are the arrival and departure delay and those flags, those 2 flags. So hopefully this finished. And what did I call it? I called it median results. Okay, so I did the, so I did the group by key. So that does the grouping to create these guys. And then you notice I put the cache in here to make sure it stayed in memory. And then the next thing I did was I said, okay, now I need to do a mapping step because I'm taking the data set that consists of all of these key value pairs as a data set. I'm basically just doing a transformation, a one-to-one transformation, where for each key, I'm going to take this as an item and compute a result, which is going to be the delays. So the size, the number of observations in the result of group by key is however many of these airline, month, airport combinations there are. And that's the same thing, that's going to be the same size after I do the mapping. So I'm not really doing any reduction here at this point because of the fact that I've done this grouping by key. And then I'm going to collect the results back to Python. So that was called median results. This is probably going to be huge. So maybe I have a hint to myself of how to just see some of them. Yes. Okay, so median results. So this is the first 6 of those. Was it called something else? No. Maybe I didn't do the collection, or maybe it's just failing on me again. All right, so again I seem to be, I didn't import, I see. When I started Python again, I didn't import NumPy, and so I'm getting errors because it doesn't know the NumPy functions. All right, so given time, I'm just gonna go through what I got when I actually ran this without getting any errors. So what I saw for the first 6 results was, okay, for Delta in August from Philadelphia to Los Angeles, the median, I don't know if this is arrival or departure, the median arrival delay was 85 minutes and the median departure delay was 108 minutes. So there actually probably aren't very many of these flights because these are very long delays, so it's probably just a small sample issue there. But you can see, here's that sort of aggregated key, and here are the 2 results that come back from calculating those 2 median values. Okay? And so that's how I would do something if I don't have one of these simple operators where I can do everything nicely in parallel and where I need to actually group into subsets and then do something. But if, as I mentioned before, if these subsets got to be really, really large and I had a lot of them, then I might run into problems of running out of memory and having really huge objects that I'm trying to manipulate here, which sort of defeats the purpose of doing things in this distributed paradigm. Okay. Questions, comments? Yeah, Mike.
Do you know why it's betting the
The U, I think, is, I need to remember my Python here, I think the U is just an indicator that it's particular text format? Send it.
Unicode.
Unicode, okay, thanks. Okay, so let me see what else I want to say here. Let me just set the stage for what I'll do briefly next time, which is the regression calculations. So let me just go back to the PDF. So this is the section 633 on fitting models. So we're gonna see a couple different ways of fitting models. I might not do all of this not do all of this on Wednesday. I might save some of this for when we start to talk about optimization, because some of this gets into different optimization techniques. But if we think about how would we run a regression on this huge data set, this data set is only huge I haven't actually told you what regression I want to run. Suppose I just want to run a regression like I did when I was using the FF package, and I just want to regress on the day of the week and maybe the distance of the flight. If that's the case, I've only got 6 or 8 or 9 covariates or predictors in my regression model. So think about if you think about building up a regression design matrix, think about what this looks like. This is going to have a zillion rows because it's got the 11 million observations, but it's only going to have like 8 columns to it. So it's a very long, skinny design matrix. Okay? And if we think about a regression, about going back to how we express regression in matrix format, we take our design matrix X, which has all the covariates 1 up to P and all the observations 1 up to N as rows, and we solve what are called the normal equations. Okay? And this Y is just the vector of observations. So if I think about the size of these guys, because beta hat is just X transpose X matrix inverse X transpose Y, if I think about the size of these guys, that's just a P by P matrix, which in this case would just be an 8 by 8 matrix, which is trivial. And X transpose Y is just going to be a P by 1 vector, 1 for each of the different covariates. Basically, it's covariance with each of the covariates. Right? So if I could actually compute these, my life is going to be really easy. So these are just the sufficient statistics in the regression problem. If I knew those, I don't have to think about doing anything in parallel, because I've just got a very tiny linear algebra problem to solve at that point. So if I did indeed not have very many predictors, then I could do that, and that's what this first example shows. Is first I'm going to do a little bit of filtering here. So I'm going to take the original observations, I'm going to filter it via the screen function. Remember last time when we did the filtering with filtering down to the SFO airport, we had the lambda, we had the anonymous function. Here I'm just doing the same thing, except I'm actually naming the function. So I'm just defining the function here. And all I'm doing here is sort of the obvious thing. I'm excluding the header rows. I'm excluding cases where the departure delay is missing, or some of the covariate, I don't remember which of these the other which. I'm excluding cases where either the covariate information is missing or the observation is missing. And I'm also, I think I maybe mentioned this last time, I'm just restricting down to cases where the delay is not more than 12 hours and not more than 12 hours and not less than minus 30 minutes, just because those are either weird outliers or just plain outliers. Okay, but once I've done that, we can think about what would it look like to try and compute these sufficient statistics in parallel, and that would be a matter of, well, I can think about this matrix as taking an individual row from that X matrix and doing the outer product of the X row with it transposed. And that will build up, then we can build up X transpose X as the sum over I from 1 to n of xi transpose. And if we can write something out as a summation like this, you immediately can think, oh, MapReduce would be a good thing to do with that, because it's the natural sort of thing that you do in MapReduce. So we'll pick up there next time. This basically just implements what I'm saying there, but in Python code, and we'll spend probably the first 10 or 15 minutes of class next time doing this. And then we'll switch over to the linear algebra unit, and I'm going to email you guys or post a note this afternoon. What I want you to do is look through the first 6 or 8, I'll say specifically in the note, pages of the linear algebra unit, because that's basically all just linear algebra stuff I'm expecting you to know, and I want you to look over it before class on Friday.